Welcome to video number 2 of our polynomial series. You have a warm-up problem there. If you'll go ahead and try to write that polynomial in standard form and identify the degree and leading coefficient. Just pause for a second, come back when you're ready. Okay, what we talked about yesterday is that in order to write a polynomial in standard form, we have to combine all of our like terms, and we have to get the largest exponent out front and write our terms in decreasing order of exponents. So taking a quick glance here, we have an x to the fourth is our largest exponent here. Nothing to combine that with, so we'll just leave that as 2x to the fourth. Now the x cubed terms, there are two of them to combine. 5x cubed plus 2x cubed give us 7x cubed. No x squared terms at all. That's okay. This just didn't have any what we call quadratic terms because of the x squared. We do have two linear terms. We have a negative 6x plus a 10x, which will combine to give us a plus 4x, and then a plus 8. There we go. So 2x to the fourth plus 7x to the third plus 4x plus 8 is our standard form polynomial. Remember, this is a polynomial because all the exponents are whole numbers. 4, 3, 1, and then x to the 0 power there. And this question also asks us to identify the degree and the leading coefficient. The degree is always your largest exponent. And since we've written this in standard form, we have the largest exponent right out front. So our degree is 4. And then our leading coefficient is right there with that degree. It's the 2. All right? What we're going to do today is take that degree and leading coefficient to help us start to look at what a graph of a polynomial will look like. There are several different characteristics of polynomial graphs, so I don't want to just jump right in and say, okay, we're going to take this whole polynomial and graph it all today. That would be pretty overwhelming. What we're going to look at today is just what's happening on the ends of the graph. You know, every graph will, either head up in this direction or head down in this direction. So you're drawing arrows at the ends of your graphs. Today we're going to look at how those arrows are going to be moving, which directions, and what we call the end behavior of a polynomial and of a graph. You have a chart on your guided notes there that we're going to be trying to fill in as we go today. So I have this same expression written out here on the next board, and I want to talk about if this were part of an equation, if this were y equals this same polynomial expression, what would the graph of that polynomial look like? And specifically today, just what would the ends of that graph look like? The two important things that we're going to use to determine what the ends of these graphs are going to look like are the two things you just identified in the warm-up, the degree and the leading coefficient. So the fact that we know the degree is 4 is going to be important to us. We're going to take advantage of the fact that there is a pattern to the way graphs of polynomials look. And that's that whether that is an even or odd exponent makes a difference, right? So when we look at the degree, when we look at the largest exponent of the polynomial, what we're concerned with on our graph, as far as the ends go, is whether that degree is even or odd. We have an even degree here. So the fact that the number 4 is even is going to be helpful to us. So let's think back. We've graphed something with an even degree before. What have we graphed? We've graphed y equals x squared, right? We've graphed, if I just said, let's think about y equals x squared here. And think, all right, well, what does the graph of y equals x squared look like? It looks like a parabola, right? It's a U shape. Now, sometimes our parabolas open up. Sometimes we've got a U that looks like that. Sometimes we've got a U that is upside down, right? So how do we know whether our parabola is opening up or whether our parabola is opening down? Right, it's whether that's a positive x squared or a negative x squared, right? So the fact that this is a positive leading coefficient is also going to matter to us. So this leading coefficient being 2 is important to us because that number is a positive number. So when we look at degrees, we're interested in whether that degree is even or odd. When we look at leading coefficients, we're interested in whether that's a positive or negative leading coefficient. So I have a polynomial here with an even degree and a positive leading coefficient. So the ends of that graph are going to look the same as the ends of y equals a positive x squared. In other words, the ends like this. Both the ends are going to be pointing up. Now, I'm not saying that this graph just looks like a parabola. That's not the case at all. What I am saying is that, if I took, we've got a graph over here. If I tried to graph this polynomial on my graph, the ends of that graph would resemble the ends of a parabola opening upward. Now I can stand in the middle, and you can't see what's going on in the middle. You can just see the ends of the graph. It's going to look like the ends of a quadratic, of a parabola. A lot of things will be happening in the middle, and we're going to have to deal with those things at a later date. We're just concerned about what the ends of the graph look like right now. So the ends of this polynomial that we've been talking about so far are both going to point up. Now, when we describe that end behavior, we want to talk about each end individually, and we want to use good mathematical terminology. So I want to talk about that now. So I want to talk about what's happening on this end of my graph, right? At this end of my graph, my x values are getting larger and larger and larger, right? We say that our x values are approaching infinity, a million, a billion, a trillion. Our x's are getting larger and larger on this side of the graph. So as that happens, as x approaches infinity, as x gets bigger and bigger, what's happening to y? Look at that arrow. The y's are getting bigger and bigger and bigger as well. So as our x values are approaching infinity, our y values are also approaching infinity, right? Here's how we're going to write that out. I'm going to put this in our chart. We have, for the first part of our chart here, we're looking at a degree that was even. All right, we had an x to the fourth power. We had a lead coefficient that was positive. Right? We know those two arrows are going to be pointing in the same manner as a parabola opening upward. Right? So we're kind of thinking those arrows are going to look something like that. Now, here's how we write that statement out. We say as x approaches infinity, and you just use an arrow for approaches. As x approaches infinity, our y values are also approaching infinity. Right? That's what was happening on our graph. As the x got bigger and bigger, the y also got bigger and bigger and bigger. But I want to talk about the other end of the graph as well. Obviously, there's two ends to the graph, so let's look at that second end as well. Let's look at what happened on this end of my graph. Over here, my x values are getting more and more what? More and more negative. So as my x's get more and more negative and head toward negative infinity, negative 10, negative 100, negative a million, and so on, look what's happening to my y values. My y values are getting larger. So as my x values are approaching negative infinity, my y values are still approaching positive infinity. That arrow is pointing up. The y's are getting bigger. Even though the x's are getting more negative, the y's are getting more positive. So in our chart, the other statement we're going to make there is that as the x values approach negative infinity, as x approaches negative infinity, my y values are going to approach positive infinity still. All right? Whether the x is getting very, very large or very, very negative, my y values are getting large in both cases. My y values are approaching positive infinity on both ends of the graph. These are the kinds of statements we're going to make about end behavior. We're not just going to say, well, they point up, or here's some arrows. We're going to state this as what happens as x approaches infinity and what happens as x approaches negative infinity. Now, what if we had an even degree, but then my leading coefficient ends up being negative? Well, now let's think about an x squared with a negative. Y equals negative x squared. Both of those ends would be pointing down. It would be an upside down parabola. Right? So the ends are going to look like that. So let's think about, well, in that case, what's happening as x is approaching infinity? As x approaches infinity now, my y values are going down. They're going toward negative infinity. So my y's are approaching negative infinity. Sorry, that's a terrible infinity. Now as x approaches negative infinity, my y values are also approaching negative infinity. Because this resembles an upside down parabola. This resembles y equals negative x squared. So as x approaches infinity, y approaches negative infinity. As x approaches negative infinity, y approaches negative infinity. Both ends have y values that are getting more and more negative, right? So when you have an even degree, I want you to think about parabolas, because that's the most basic kind of even degree polynomial that we can graph, right? So now what happens if we have odd degrees? Happens if our degrees are odd. Again, we'll get different scenarios, whether we have a positive leading coefficient or a negative leading coefficient. And I have an example here that we can look at. Took care of that one. Let's look at this graph of a polynomial. If we were trying to graph y equals 2x cubed minus 5x squared plus 7x minus 10. Look at your degree. Your degree is odd. Your leading coefficient is a positive 2 for your leading coefficient. What I want you to do now is think back to the easiest odd polynomial that we've graphed. And you may think, well, we haven't done x to the third or x to the fifth or anything like that. We've done x to the first. Right? X to the first is just a regular linear function. It's a regular straight line, like a y equals mx plus b. So when you see an odd degree, I want you to think, hey, this is a whole lot like a straight line, right? Well, I know what the graph of a line looks like. Obviously, it's either going uphill or going downhill. How do I determine whether that graph's going uphill or downhill? I think about the slope, right? The slope, which is your m, which notice is the leading coefficient of that line. And we never really called that a leading coefficient. We just said it's the slope. But that slope was the thing that told you whether your line was increasing, going uphill, or decreasing, going downhill. So in this case, I have an odd degree, so I'm thinking about straight lines. So I see my odd degree. I think the ends are going to look like a straight line. The positive leading coefficient means the ends are going to look like a straight line with a positive slope. So this end and this end are going to be your ends of your polynomial. Again, I don't know what's going on in the middle. This isn't the graph of a straight line. But the ends are going to look like the ends of a straight line with a positive slope. So look, what's happening is x is approaching infinity here. Y is approaching infinity. Y is getting bigger. What's happening as x approaches negative infinity? Y is approaching negative infinity, right? Y is going downhill. As x approaches positive infinity, y is also approaching infinity. I'll put that in our chart. As x approaches infinity, y is also approaching infinity. That end of the graph is getting larger. Now as x approaches negative infinity, as the x values get more and more negative on your graph, your y values are approaching negative infinity. Right? If you've got an odd degree with a negative leading coefficient, just think about a negative slope line. Right? So the arrows were pointing this way for the positive leading coefficient. The negative leading coefficient, the ends are going to look like a downhill line, a line with a negative slope. Again, not necessarily the middle part, but the ends. So in this situation, if I think about this on a graph, as x approaches infinity, right, as x gets bigger and bigger and bigger and bigger, y is getting more and more negative. Y is approaching negative infinity. As x approaches negative infinity, more and more negative, y is going to get larger and larger. The graph, the y values are approaching positive infinity. So these are all the scenarios that you're going to see with end behaviors. We're going to practice these in class tomorrow. We're going to get to where we don't need this chart anymore. We'll just think about even degrees look like parabolas on the ends, odd degrees look like straight lines on the ends.